Hello, so today we'll be talking about Lab 3 black hole orbit. The lab objectives are that we are given position, time step, and mass of a star, which is orbiting a black hole. We're also given the black hole's position. The black hole mass is unknown, and we're going to obtain it via Newton's second law of universal gravitation. So we're going to do this after analyzing the given data according to the positions and etc. A computational model of the star's orbit around the black hole will be shown, and then we're going to answer what if and what does it mean questions. So what we know is that we have the position XY positions from the star from the CSV file. We know the star mass, we know the time step for a day on Earth, and the black hole position. So now we need to calculate the black hole mass. So the result of this was 4.8 to 5 E31, the 31 power, and that's in kilograms, should be here. Okay, so these are the formulas that we'll be using. So we have magnitude of F net is equal to gravitational constant G times m1 times m2 divided by absolute value of r squared, which is the distance. So we're going to change around Newton's gravitation formula to get the second mass, which is the black hole mass. So we have magnitude of net force times absolute value of the distance squared divided by gravitational constant times mass 1. So r is the distance between the center of the masses of the star and the black hole. Oops. Okay, some more formulas. So distance r is equal to r2 minus r1. Magnitude of r is square root of x squared plus y squared plus z squared, which is just 0. Using Newton's second law to calculate F net is equal to change in momentum divided by change in time, which is the momentum principle. I'm going to use a small delta t to assume no change in force. So we're going to break down Newton's second law to the momentum principle into the parallel F net parallel and F net perpendicular components. So F net is equal to F net parallel plus F net perpendicular. F net is equal to dp divided by dt. So change in momentum divided by change in time is equal to the change in the magnitude of the momentum divided by change in time times the direction of the momentum p hat plus the magnitude of p hat times change in p hat divided by delta t. So change that's that, and so that those are the parallel and perpendicular respectively. So now we're going to take a look at the code and then run the program. So here we set up the visualizations. We added the black hole in the center. See, we initialize the properties. This is the black hole position at the origin, star's mass, delta t time step for 1 day in seconds. This is when we start our clock. These are, we're initializing the list that they're going to hold the x and y components for the velocity. So the first thing that we do is this first while loop calculates the velocity, the x component of the velocity, and then the y component of the velocity, and then the second while loop here. First we get the velocity components for v initial and v final, and then from that we get the momentum components such as p initial and p final, which is the star mass times the velocity for each one. And so then from here we have change in velocity and change in momentum. And then now we can calculate dp divided by dt, which is F net. We assign that here. And so then here we break it down into the parallel and perpendicular. And then from there we have F net perpendicular is equal to change in change in momentum times change in time, the perpendicular component of F net. Okay, this is the gravitational constant. And here I asked it to, at the end I asked it to print out the black hole mass, which this is the formula here. It's the magnitude of the net force times the distance squared divided by gravitational constant times the star's mass. Okay, and for the output, we're going to see basically the yellow arrow is the net force, the blue arrow is the F net perpendicular, and the black arrow is F net parallel. So we're going to run this. Okay, so now we're going to answer the what if and what does it mean questions. So what makes F net and its parallel perpendicular component similar and different from the dp divided by dt formula? So basically they're equal to one another, so they're the same, and they're different because they're derived differently. The F net involves the gravitational formula, and the dp dt involves a change in momentum and change in velocity. So what does it mean? If there was a new black hole but the star motion data was the same as before, could you tell the difference? No, because all the calculations would be the same if they're using the same motion data, and so we could find the same mass for this new black hole. Thank you for watching.